So I'm Jimmy from Spotify, and today I will talk how we're using Cassandra at Spotify. At Spotify, we're not afraid of failing. In fact, our founder, Daniel Ek, once said, we aim to fail faster than anyone else. And the reason is, every time you fail, you learn something. So if you fail faster than everyone else, you will learn faster. And we have failed many times with Cassandra. So last year in the Cassandra Summit in San Francisco, a colleague of mine, Axel, had a presentation that he called How Not to Use Cassandra, where he summarized all our failures with Cassandra. But as I said, we learned a lot, and during the last year since then, we have managed to run things much more smoothly. So today I will talk about how to use Cassandra. I've been worked at Spotify for 4 years as a software engineer, and worked with Cassandra from a developer's perspective. And then I worked in a team working with the Cassandra infrastructure at Spotify, and now I'm the tech product owner of that team. You can follow me on Twitter if you want to know more about what's up with Cassandra at Spotify. So yeah, some words about Spotify. We have 50 million monthly active users, 12.5 million paying subscribers. We have a lot of songs, we have a lot of playlists, and we have a lot of data that we store in Cassandra. We're also available in 58 markets all over the world. So I will talk about three things today. First, I will talk how we run Cassandra cluster at Spotify, how our architecture looks like. Then I will go a bit more technical and talk about repairs and all the problems we face with repairs. I'm sure you heard about some of those already today by other talkers. And then I will talk a bit about data compaction, which was added to Cassandra just a month ago, and Jonathan Ellis talked about it this morning. It was we invented at the Spotify office. So Spotify was released about 6 years ago, and one of the first challenges that we had, and that caused the first infrastructure team at Spotify we created, was how do you store data reliably for 500 million active users? And we call this problem the storage problem, because we talked about it a lot. Today, a solution might be we can just use a cloud provider and use some database in the cloud. Unfortunately, back then, the cloud providers or the services they have provided were not up to the quality we wanted. You should remember, one of the most important features of Spotify when we released it was low latency. If a user double-clicked on a track, you should start playing it right away, within 200 milliseconds. And the cloud services couldn't provide that quality of service, which meant we decided to build our own data centers, which also means we need to host our own database. So which database should we use? During these early years, we tried a lot of different things. Relational databases, they were very robust, but don't scale so well. We tried MongoDB, doesn't work so fine in production, and a lot of other databases that just didn't work well, were crashed or corrupting data and whatnot. We even tried out some concept called home siting, so you only store the data for a user in the data center where his account is created, but that, of course, has other problems. You don't need to replicate between data centers, but if the data center goes down or becomes unavailable, well, that's poor users. And so we found the Dynamo paper, which is a famous paper written by Amazon in 2007, and they described a very interesting replication model that we liked. So we started to build our own database based on the Dynamo paper, and that was also a horrible failure. But then we found Cassandra. It seemed also based on Dynamo, and it seemed to have everything we actually wanted. It had the internal storage within a node was very robust. It used log structure storage, immutable files. All these things make it very unlikely that you would have end up with corrupt data. It also has very important features that it has multiple data center support as a built-in first-class citizen, which meant the whole home siting concept that we were worrying about, we don't have to bother about that. We can just fairly easily replicate data across data centers. So we started playing around with Cassandra. This was the first version we tried out, was version 0.6, I believe. And the first service at Spotify that used Cassandra was a playlist service, which I talked about last year when I was here in London. The playlist system is an interesting system. As I said, we store 1.5 billion playlists, and they are all stored in Cassandra cluster. Even today, that's our biggest Cassandra clusters, actually. And yeah, we made many mistakes in the beginning when running Cassandra, and you can hear all about them in Axel's talk. If you haven't listened to that one, I think it's still available on Planet Cassandra. We had spent a lot of, many of the mistakes were operational mistakes from our point, but there were also many bugs in the early versions of Cassandra. It was essentially a pretty immature database back then. This was 4 years ago. But despite all these problems we had, there was this one thing. We never, ever lost data. We could have problems with data becoming unavailable at times when the cluster was overloaded or other problems during upgrades, but the data was always there. We never lost data, which was kind of why we liked Cassandra in the first place. And all the problems that we had, we could fix them, either learning ourselves or fixing bugs in Cassandra. So as the years progressed, Cassandra grew more and more mature, and we started to use Cassandra more and more at Spotify. So today, Cassandra is actually the database most teams choose when they want to store data, then want it to be highly available, and to serve a lot of end-user requests. So today, we actually have 80 Cassandra clusters at Spotify, more than 80 Cassandra clusters at Spotify, running on 650 plus nodes. We're running Cassandra 1.2 and 2.0. Still haven't looked into 2.1 yet. Our largest cluster is 60 nodes spread out on 2 different sites. And we have data centers in 4 geographic locations, 2 in the US, 2 in Europe, and we run very many multi-data center clusters. Typically, we replicate between 2 and 3 data centers, depending on latency requirements and other things. We had some problems when running in 4 data centers, but I will talk more about that later. And we have a fairly standard Cassandra setup. We're running on physical hardware, our own physical hardware, with many CPU cores and lots of memory. One thing that we're not using in Cassandra, which I would like to talk about, is that we're not using vNodes, which I like to bring attention to. vNodes is, as you may know, standard today. It's enabled by default. We never really use them because we think they don't provide enough value for us. So the main reason you would use vNodes is that the bootstrapping process of when you're replacing nodes is much faster. The thing is, since we're running on physical hardware, our nodes, machines seldom actually break. So we don't have to bootstrap nodes very often. We can sometimes have to expand clusters, but as you will see, we actually don't expand clusters that much either. We actually have very many clusters instead. A much more common thing we do is actually restarting clusters. And if you restart clusters, if you're running vNodes, you can only restart 1 node at a time. Because if you pick any 2 nodes, chances are they will almost certainly share data using vNodes. If you have not using vNodes, you can actually start multiple nodes in parallel if you know what you're doing and make sure that they don't overlap in token ranges. And yeah, in general, so another reason you might want to use vNodes is to simplify token assignment when spinning up new clusters. But we solve that by having our own tools for automatically spinning up Cassandra clusters. So some of you might wonder, okay, so why do Spotify have 80 Cassandra clusters? It seems a lot of overhead and quite a lot of work to manage all those clusters. So when we started 6-7 years ago, we were not so great at databases, but one thing we did get right from the very beginning was our microservice architecture. Without it, I don't think we would be where we are today. So what is a microservice architecture? It means that you have very many small services in the backend, and each service does one thing and one thing only. This allows you for developers to develop independent on each service, and you can iterate much faster by only working on your services and deploy the code faster without synchronizing so much with other teams. So it allows faster development. Another great benefit of it is that if something goes down, you will only affect a small part of the entire Spotify service. And for this to work in practice, it also means that each service needs its own database. Otherwise, if you would if distinct services sharing the same database, if some team deploys a new version of a service, and that one suddenly starts sending twice as many requests to the database because of some careless developer, you might bring down the entire database, causing other services to be brought down as well. And you don't want that. So that's why we have, for each of these backend services where you need to store data, we make sure that it has its own dedicated Cassandra cluster. And there are even more advantages, but of course there are some drawbacks to this as well, and that's the overhead of maintaining so many Cassandra clusters. And therefore I would like to talk a bit about operational responsibility. So up until last year, we had a single SRE team dedicated and that were responsible for making sure that the Spotify service was running 24/7. Developers could always push the code into production, but it had to sync with SRE, say, yeah, now we're deploying some new code. But if the service, Spotify service crashed in the middle of the night, it was some poor guy in the SRE team that had to get up and fix it. And considering that we had, by this time, had a lot of hundreds of backend services, there were a lot of things he had to keep track of. And that didn't scale so well. So instead, it was decided that, OK, so the guys who best know the code is, of course, those who have developed it. So they should, if you can make them operationally responsible for their own code, we can spread the load, spread the pain, and perhaps even make uptime better. So this was something we changed in the middle of last year. And the new mission for the SRE team was to simply enable all the other teams at Spotify to be able to do this, to make them autonomous, to make them be able to deploy code fast and also learn how to handle on-call and all that kind of things. We still want to iterate very fast. And if you are a developer and deploy code and know that if you break something, you have to wake up in the middle of the night to fix it, you're very careful with what you're deploying in production. So what does this mean for the Cassandra team? Same as with the SRE team, there was a centralized Cassandra team responsible for all the Cassandra clusters at Spotify, including setting up new clusters, upgrading them, expanding them, and so on. Typical DBA work, and also, since Cassandra was quite immature back then, a lot of time was spent on working on upstream Cassandra tickets and doing hot patching. After this, the change in operational responsibility, suddenly the feature teams were now responsible for their Cassandra clusters. And we, the Cassandra team, were now instead responsible for providing the tools and building proper tools and educating and providing support for the team so they can operate their Cassandra clusters. We're not expecting all the feature teams at Spotify that use Cassandra to become Cassandra experts, but we do expect them to run the day-to-day business and understand when the cluster is working fine and how to use our tools to expand clusters, set up clusters, and so on. And if something is going wrong and they can't figure out what it is, we're always there to provide support. The important difference is that they come to the Cassandra team and ask, what should we do now, rather than us proactively monitoring all these 80 Cassandra clusters, trying to figure out how to best to improve performance. So how has this all turned out? It's actually, when this bet was, when we decided to take this decision, we expected short term that we would have the uptime of the service would go down, but actually the opposite happened. Which was a very pleasant surprise. And it really shows that if a developers have to maintain their own code in production, they become much more careful and build more proper tools and does more testing. And as far as it comes to Cassandra, we had no serious Cassandra incident for this entire year. There might have been some short, not everything I worked all the time, but there's been no data unavailability in the same scale as we had before. We could also attribute this that Cassandra is a much more mature database these days, obviously. I'm not going to lie and say everything has been unicorns and happy faces. There are some of the teams, in particular those that are not the biggest user of Cassandra at Spotify. They don't feel like they want to spend time learning Cassandra for something they don't use so often. So we're looking right now into if we can do some middle ground as a Cassandra team at Spotify to provide storage as a service internally within Spotify for some of our users where it makes sense. For the heavy Cassandra users of Spotify, those teams that store a lot of data in Cassandra, they are already pretty good at Cassandra, can handle their own clusters very well themselves. So that's operation of Cassandra cluster at Spotify. Now I want to rant a bit about repairs. I won't go in and explain what repair is. I'm sure you all know about it. It's the only external operation you need to carry out on a Cassandra cluster and manually run to make Cassandra behave the way it should behave. But it's also the thing that's caused us most pain the last year or last couple of years. Let's first look at why do you need to run repair. There are a couple of reasons why you need to run repair. First, if you're deleting data, you need to run repair regularly to avoid old data resurfacing again. And I mean, you have probably heard this many times today already. Aaron talked about it just before me here. So I won't go into that. There's also, if you want your cluster to be eventually consistent, which I'm sure you want, you need to run repairs. Let's say you have a multiple data center and you have And then you're probably using consistency level local 1 or local quorum, because you get the good trade-offs between consistency and availability. And so if you have one user writing data in one data center, and then there is some kind of partition split between your data centers, something that happens quite often across the Atlantic, you want the data to eventually end up in the other data center. Otherwise, users in US won't be able to see what users in Europe are writing and so on. There's actually a third reason, which might not be as obvious, and that's you can actually lose data if you're not running repair, if you're changing your network topology. And with that, I mean if you're replacing nodes or if you're expanding your cluster, you have to run repair quite a lot when you're doing that. Otherwise, you might risk losing data. And I want to show this with an example. So here we have a Cassandra cluster containing 6 nodes. We're assuming replication factor 3. We're assuming all the reads and writes are done using quorum consistency level. So we have some data that's stored on node B, C, and D. But for some reason, node C, the red one, contains old version of the data. And that can happen for any number of reasons. And the quorum reads still work. You're always ensured that you will read the latest data, because you will always read from node B or D. But let's say something happens with node B. Maybe it just crashes, or the hardware failure, or you want to upgrade the hardware or do something. Then you need to you will insert a new empty node that bootstraps from one of the other nodes in the ring containing the data. And if it happens to get that particular data from node C, you will suddenly end up with 2 nodes having the old version of the data. And all of a sudden, the quorum reads may return old data. And to make things worse, if the next thing you're doing without running repairs is replace node D, you will actually lose data. So this is obviously very bad. And what this means is that you actually have, if you for instance, are upgrading all the machines in your cluster, you actually need to run a repair on all the nodes after replacing every node. So if you have a 10-node cluster, you need to run repair 10 times if you want to replace all that hardware. This can be quite time-consuming, and you must be able to run repair consistently without failing. And as it turns out, that's not so easy if you have large Cassandra clusters. So what has gone wrong with repair? Why is repair so hard? There have been many bugs in the code that does the repair. Many of them we fixed, but there are still problems. I would like to highlight some of the problems that we've encountered over the years. So repair consists of mainly 2 phases. First, you calculate the Merkle trees on the nodes, and then you find which nodes contain mismatching data, and you stream data between them. The problem, for the longest time, there was a problem in the streaming. So if the stream was disconnected, for instance, if you stream data across the Atlantic, you can easily get disconnected, that the stream just stops. The problem is that the repair coordinator wouldn't get notice of this. The repair coordinator would just sit waiting for the stream to finish, and it never happened. So you had to abort the repair through JMX. This was, I think, fixed in 2.0. The entire streaming protocol was rewritten to 2.0, so this should be a solved issue now. Another problem with repair is the concept of overstreaming. So what does overstreaming mean? It means that so when you're calculating the Merkle trees, there's a limited granularity of the Merkle trees. So if you store a lot of data on your nodes, even if there's only one row mismatching between 2 hosts, you might still end up streaming hundreds, if not thousands, of rows if you have a lot of data. And if you have thousands of rows that are out of sync, you can end up streaming really, really a lot of data. So we had clusters storing 100 gigabytes per node, but when running repair, they were sent 200 more gigabytes. So the life size of the node went up with a factor of 2 or 3 in just a short period of time, and that, of course, killed the entire cluster. Started compacting like crazy, performance went down the drain. So the solution, and this is still a problem, which is why you might not want to run node to repair -PR or just node to repair if you're storing a lot of data, because you will have this problem if data is out of sync. So the solution was the introduction of sub-range repairs, introduced in Cassandra 1.1.11, which allows you to repair smaller parts of the cluster at a time. So you can, instead of running repair node to repair PR, you run node to repair and specify a small token range. This allowed the granularity becomes much more fine-grained, and you don't stream more than necessary. The problem with this is that it's much more tricky to actually run the repair. Instead of invoking one repair command per node, you need to invoke repair maybe 100 times per node with different parameters. So it gets much more cumbersome, and you probably need to script this up. And there are scripts out there that does this. The problem is combining this with many of the other problems with Cassandra repair, it can get quite messy, and you don't want to do this manually, especially if you have 80 Cassandra clusters. more problems. Performance. So when you calculate a Merkle tree, you're essentially doing compaction, which means that on all the nodes that you calculate a Merkle tree on, it does so in parallel. At least it did so in parallel by default in version 1.2, which means that if there's a request to any of the keys in the part you're repairing, that request will end up on a node doing a heavy compaction. So some part of the cluster will always have performance degradation, and that can cause problems. So the solution here was introduced in Cassandra 1.2, called snapshot repair, or also called sequential repair. It's the same thing. It's a clever idea. So the idea is that they add a new phase to repair. So the first thing when you invoke repair with snapshot repair, which is actually default in 2.0, so you don't even have to specify it, it takes a snapshot on all the nodes where you need to calculate the Merkle tree on. The snapshot is very fast in Cassandra, just hard link files. Then it calculates a Merkle tree on one node at a time in parallel on the snapshot rather than on the live data. So this is very clever in theory. Problem was that first it had a lot of bugs. For instance, there was one bug that it didn't take the snapshot on the coordinator node. It took snapshot on all the other nodes except the coordinator node. So the snapshot mismatched. And another problem is that it's actually a lot of overhead in opening the snapshot. If you're running level compaction in your cluster, you can easily have thousands of SS tables. And the snapshot will contain thousands of SS tables. And you know, if you start Cassandra and have to read in all the metadata but from thousands of SS tables, that can take a long time, easily several minutes, depending on how fast your disks are. And again, so if you have this overhead of just opening the snapshots, and you have calculating Merkle trees as sequential, and combining this with that you're running sub-range repairs to survive, it adds up to a lot of overhead. In practice, this makes running snapshot repaired on large data when using level compaction it's not really doable even right now in 2.0. There are patches in upstream Cassandra to fix this. One is in 2.1 that actually only snapshots the part of the range that you're repairing. So even if you have thousands of SS tables, you only snapshot those SS tables containing the range you need to repair. There's also a patch that we submitted, which hasn't been reviewed yet, that fixes this in 2.0 in a different way. And even more problems with snapshot repair. There's actually so this Cassandra ticket 8193 is a performance improvement. So if you have 4 data centers and each data center have replication factor 3, you have 12 replicas. If using snapshot repair, that means calculating 12 Merkle trees in parallel. So it takes 12 times as much time than doing parallel repair. So the idea with snapshot repair is nice, but why do you have to calculate the snapshot just one node at a time? We can actually do it one node per data center at a time. So this is a new improvement in Cassandra, which will actually, I believe, will be out in the next version, Cassandra 2.012. So you can specify a DC-aware snapshot repair. And yeah, there has been more problems, but I don't want to go through everything. So when they now introduce this incremental repair in Cassandra 2.1, I don't even want to think about what new bugs they introduce. Let's say I'm not going to try it out for the next couple of months at least. It seems very scary to me. Conclusion, repair is very hard to run on a cluster. It's on a large cluster, particularly if you're running a multi-DC cluster and using level compaction. If you don't have all this, yeah, it might be doable. And I really recommend that you design with this in mind. For instance, if you're deleting data, if you can make it so that if old data reappear to only be very bad and not a total disaster, that's great. Maybe not, you can't do that. Try to be repair smart. Do you actually have to repair all your tables? Maybe you only have to repair some of the tables because of data modeling reasons. There are other tricks. You can do local DC repair. You can do pairwise DC repair to minimize the damage and make it easier for the repairs to finish. And as I said, we have a lot of Cassandra clusters. And getting this to work when you have a lot of Cassandra clusters and the repair never finished by themselves, you need to build a lot of tools. And so something we did very early on at Spotify was build these tools for automatic repair management. The first version of the tool didn't use sub-range repairs because it was made before sub-range repairs. It has some nice features. You can repair multiple nodes in parallel if they don't overlap each other in token ranges. And it also detects hanging repairs and so on. We never open source it, unfortunately. But I'm glad to say that we're just starting working on on a new tool, which actually is a much more improved version, using sub-range repairs and so on. We named it Cassandra Reaper. It was a misspelling of repair, but it's kind of funny because it ensures that your dead data stays dead by distributing tombstones. We thought it a proper name for a repair utility. This one is open sourced and is still early in development, but I recommend you checking it out. It will be pretty awesome, I think. Another thing, we create also a lot of tools just check what's going on with repairs. So one of the nicer tools, I think, useful one is SP Cassandra Repair Stats that just essentially scans the Cassandra log file and just groups all the information about the ongoing and historical repairs. So you can easily see what's going on, how long time things take, are there streams hanging, how long is each phase taking, and so on. There will be links to these two later on. And that's about repair. So I would like to round this off with talk a bit about data compaction. It's new since Cassandra 2.11 and 2.1.1. As I said, it was developed internally at Spotify as a master thesis project, and it's now seems to be very popular, or very many people wonder about it. So I will talk a bit more about it. Jonathan Ellis did an excellent explanation of it this morning. I would like to add some more things about it. So size-tier compaction and level compaction has been around for a long time. And there are some use cases, though, where neither of them are a perfect fit. And ironically enough, that's actually time series data, which is one very popular use case for Cassandra. So if you're using time series data and with size-tier compaction, you can end up in a situation like this. And each green bar here represents an SS table. So we have 11 SS tables. The left and the right end represents the minimum and maximum time span that the SS table contains. And the problem with size-tier compaction is that it doesn't, when it compacts, it doesn't take into account the minimum and maximum timestamps. It only it picks SS tables based on file size. So you can get a real mix of old and new data. So you can end up in a situation like this. So this is taken from one of our clusters at a sample run. So if you do a range slice query, and the yellow box here indicates that we want to do a range query picking data between those two times, chances are you actually have to read from all of these 11 SS tables, because most likely, if you have time series data and you update all the rows all the time, which is a common use case for monitoring, for instance, you will actually have to read from all the rows. All the SS tables contain the partition you're looking for, and the data and the range you're looking for is also contained in all the SS tables partially. So you have to read from all 11 SS tables, which is not very good. So this got us thinking a bit, can't you improve this in some way? And so we came up with this idea for a master thesis project end of last year. And so this was really the birth of the data compaction structure, which Jonathan explained. I was going to explain it here, but since Jonathan had a much nicer animations than I have, so I will actually skip that. Instead, I will show you how the end results look like. Comparing the previous pictures, you now get something pretty like this. Again, you have a lot of SS tables, but they're not overlapping in time. So the slices, the windowing becomes larger and larger in time as you go getting back in time. And if you do this same range slice query, you only, in this case, have to read from 3 SS tables, which is much more nice. There's actually another use case where data compaction can provide much more value, and that's if you're storing TTL data. And in particular, if your column family or if your table only store TTL data, and that TTL data is TTL with the same value. Because what data compaction will do for you then is that since it groups the SS table by date, the oldest SS table, at some point in time, all that data will right away become expired from the TTL. And since that's the oldest SS table and there is nothing older, it can drop the entire SS table, just like that. So it's a very efficient way of getting rid of tombstones. And we're actually using data compaction in production right now for a cluster that in this particular use case. And it works very well. To summarize, data compaction, it's production ready. We're using it in production today. And some of the, as Jonathan mentioned, the default parameters, you might have to tweak them a bit still. We're working on that, figuring out what works best. Some best practices, though, is you probably want to disable read repairs and maybe also hinted handoffs. The reason for this is that data compaction works best when all the data you're inserting are with the current timestamp. With read repairs, you will get scattered inserts of old data because of the way read repair works, which makes SS table that you generated not be perfect. And you still, of course, probably have to run anti-entropy repair. That should, in theory, work better because you're doing big bulk inserts, so the damage is not as big. But this is all still, the exact consequence of this is still, we're testing this out, but we're using it in production. If you have any of these use cases, I really recommend that you use it as well. And if you want to know how it goes, follow me on Twitter. And that was it. These are some links to open source projects that we've recently open sourced. And yeah, are there any questions? Questions back there?
You mentioned generally a problem where you're saying you work fine with 3DCs, but 4DCs you had a problem with
multi-DCs. Yes, sorry about that. So the question was, we had a problem when using 4DCs. It all has to do with when you're running repair, you're comparing. I like to say that Cassandra scales linearly within a data center, but scales quadratically when it comes to number of data centers. I'm not sure it's technically true, but the thing is so when you have 3 data centers and 3 replicas, you have 9 different pairs, 9 different to compare. 9 different nodes that need to compare data. With 4 data centers, you have 12 different nodes that need to compare. So you have 144 pairs that could all possibly get out of sync. So even if there is just small difference across all these 12 nodes, it kind of grows, not exponentially, but quadratically rather than linearly. Again, with the use of sub-range repairs and everything, yeah, maybe it's more doable. But yeah, we're actually using 4 data centers, but we're trying to limit it a bit, and only when necessary. Okay, one question there.
How often do you run repair when you're not changing the topology?
As I said, if you're deleting data, you should run repair before, according to the GC grace time. We actually, I believe, we have fairly few clusters that actually delete data. So I must admit that we have some clusters where repair hasn't been run for a long time, because the data model has been such that we can survive anyway. And as I said, we don't replace machines very often. So we've been lucky in that regard. Hopefully, with this new tool, we will be actually able to carry out repair on all our clusters in a safe manner. OK. Thank you, everyone.